I'm from Princeton, and today I'm presenting some work I did with my colleagues on managing mobile network resources across environments and preferences.
The microphone is not in your. Just
What?
bring it towards you more.
Okay. Better?
Thank you.
Yep. Okay. Network usage on today's mobile devices make demands on resources which are in limited quantity. So the first and foremost would be cellular data, where most users have some sort of cap that if they go over, they'll have to pay more. Battery, while not directly a network resources, is affected by lots of use of the network, especially on the high-powered cellular networks. And performance can be affected when you have many apps running at the same time, which are using the network, causing congestion, and then ends up with a poor user experience. Further complicating network resource management is demands and conditions are not static. So obviously these devices are mobile. The user can be moving between indoors and outdoors using different connection technologies such as Wi-Fi or LTE. And even solutions like multipath networking or network migration can sort of help ease these, and we'll take advantage of this in this work. User interest also plays a role here, where the user switching between applications, what's in the foreground, what's in the background, and whether it's interactive or streaming should affect how the network resources are allocated. Finally, there are several actors on the phone who have conflicting interests. So the primary actor, of course, is the user, but their interests may conflict with applications that are running. So a user may be data sensitive or battery usage sensitive, but applications mainly prioritize performance, making sure that they get the most out of whatever they have and doing it at any cost. Also, applications can conflict with other apps, and it's up to the user to sort of moderate this resource usage. So let's look at a few of these conflicts. So here's the first one between a user and application, which is a streaming music app, sort of like Pandora or Google Music. And you can see here the user wants to reduce their cell usage, and they're okay with sort of sacrificing a little bit of music quality to get it. Unfortunately, the way streaming music apps mostly work is they try to use as much as they can so that they can preload a bunch of songs and keep playback to be seamless and the user experience good. Here we have a conflict between two apps. So our streaming music app here opens up two flows, while the video app only opens up one flow. So over time, their network usage will look something like this. And this can be a problem because of TCP only guarantees flow level fairness and not like application level fairness. So in essence, this streaming music app is getting twice as much usage out of the network. One other conflict here between interactive apps and streaming apps. So you may have a browser that sends smaller burstier requests, but they want them to be handled quickly so the user can see a fast page load. But they get caught behind a long queue of packets from these streaming music apps, which inflate the page load times. So how do current mobile operating systems sort of deal with this problem? Well, one is they allow the users to sort of micromanage across many settings menus at the operating system and application level. So this requires the user to sort of monitor and estimate what their usage is and whether they can continue to do it within their goals, which might be over periods of times as long as a day or several days in terms of a bandwidth limit. And also, it typically restricts to all or nothing, where you either can allow applications to be on the cellular network or not, but there's no real coarse-grained granularity there. Applications also come with settings, but often, even across similar apps, the settings are poorly reused. So for every music streaming app, I have to set what quality of music I want. There's not just one place to do this. They expose varying levels of control, some of them with many options, and sometimes it can be overly complicated, and some with only very few. Additionally, updates to the application can add, remove, or change the way the settings are set up, which means the user has to continuously monitor this. Another solution usually taken by iOS or Windows Phone is to limit background activity to sort of help ease these network problems, and only certain class of applications can run in the background. This leaves the user with not as much choice over how they want their device to be used. So even if they wanted this random app XYZ to be used in the background, they can't if it doesn't fall into a correct category. So that brings us to our solution that we're talking about in this work called Tango. Tango is a framework for mobile network usage management through programmatic policies. User and applications preferences are encoded in what we call policies, where the user preferences are given top priority, but applications are still allowed some flexibility. Tango addresses resource conflicts in a proactive manner, and we'll look at more what that means in a bit, and is built with network migration and network multipath support in mind. So here we have a high-level diagram of how Tango works, and this is sort of a cycle that starts from the bottom left and goes around to the bottom right. In our prototype, this is run on a periodic basis, although we can imagine it could also be done in an event-based manner. There are a couple of key primitives to know to help make this diagram make more sense. There's state, which are metrics and information from the kernel that tells you about the current device and operating conditions. There's policy, which takes this state in, does some computation on it, and generates plans of actions that which are used to sort of manipulate the state to get to a better state according to those plans, or those policies, sorry. There are three components that we're going to look at next to Tango. They are the controller, the user policy, and the application policies, and they roughly correspond to these areas. So first, starting with the controller, this controller runs as a system service, and it's in charge of gathering the device state, executing the user policy, and then manipulating the device state when it gets back actions from the policies. It does this through kernel APIs and system tools. Tango policies, obviously a key part of our thing is what a policy is, and in this case they are programs that are written to accomplish an entity's goal, where we have two levels of entities. First is the user level, and then there's the application levels. We're going to look at the user level policies first. So the user level policy is in charge of global management of network resources. So this means taking care of things of choosing which network to currently use, assigning usage metrics to those networks, whether they're limited or unlimited, and providing priorities. It also takes care to run the user policy, which sets resource constraints on the application policies on which resources they're allowed to use. Finally, it also provides a default plan for any application that doesn't register with our system with an application policy. This can also be used across classes of applications. Since policies are written as programs, we don't necessarily expect the end user themselves to write it, but rather what they would do is hook into an ecosystem where developers have written these policies for users to load onto their phone. You can imagine this ecosystem would have some metadata associated with each policy, like what its high-level objectives are and what group of applications it works best with, and then the user could decide which one they want to load. So how do we actually turn state into actions? So here we start with a snapshot of what a state might look like on the device. You can see it's currently connected to the cellular network. The battery is about half full, and there are a couple flows labeled 10, 11, and 12 on the device. This is obviously not all the state that we can expose, but here are some more examples that we have in our prototype. You can see that we go across several layers of the network stack, as well as other sources like the battery. This state is inputted into the policy, which does some computation and outputs a plan that looks something like this. Here you can see the first couple actions are migrate actions, and what they do is they're saying to move these flows 10, 11, and 12 to the current active interface, ETH0. At the bottom, there's another action called rate limit that says ETH0 should be rate limited to 500 kilobits per second. So in essence, this policy is looking at the device state and saying, I want to use the cell network, but only at a limited amount, and I want to make sure all the active flows are currently on that interface. There are other actions that we support in our system, and you can see that they can act on either interface or flow level. Only the user policy is allowed to act on the interfaces because they affect all the other apps, and you wouldn't want a third-party application doing something like that. And we include things such as enabling and disabling interfaces, rate limiting either interfaces or flows, and migrating flows from one network to another. In addition to the user policy, Tango supports application policies. These policies run in an application's process space, and the application registers with the controller saying, hey, I have a policy I would like to run. By running in the application's process space, it is able to leverage local state information of the application. For example, if it's a streaming music app, it can look at how empty or full the current playback buffer is as part of its input. Apps are naturally only allowed to perform actions on their own flows, and they only get state that's associated with their flows. They aren't allowed to perform actions on either interfaces or other application flows. They are subject to the constraints generated in the user policy, which sort of limits their resource usage, and they can also provide hints that can be incorporated in future round state. So let's talk a little bit more about what we mean by constraints and hints. Constraints are used here to proactively address resource conflicts. An example of a constraint might be the user policy tells the application, you can only use the cell network when the Wi-Fi network is not available, or if it was a little more flexible, you can only use the cell network at a certain speed if the Wi-Fi network's available. This allows the application to know what networks are available and what kind of usage it would get on either one. And this is done before the application policy actually is run. We do this to simplify the controller and app policy interaction cycle. You can imagine if we just let the application send back the plans that they wanted, there would be conflict either with the user or with each other, and then the controller would have to go back to them and say, here, you need to correct this. And that would take a little bit longer of a cycle, and it might be harder to do. In addition, apps can also hint at desired resource needs for future rounds. So if an application notices that it may need a higher bandwidth in the future or a higher network priority in the future, it can request that, and if the user policy allows, it'll incorporate it. So let's go over an example of how this might work between the constraints and hints. So on the left here, we have a pseudocode of a user policy. There are two. These are actually what a policy would look like, except in programming language. The first function, evaluate, is where the user policy takes in the state and does some computation to generate the plans, either for the interfaces or some flows. It's not really important to the constraints here, so we've omitted it, and we're just going to look at the gen constraints method. Here, the gen constraints method takes in the state. It goes through all the applications in the current state, and when it finds the foreground application, it puts in a constraint that says this application gets the high network priority. You can see this being desirable since if you're using a browser or something you want to keep interactive, you want its network usage to go first. But that's not always the case. It's not always that easy. For example, a music streaming app may want high network priority when its buffer is running low, but is okay with normal when it's not. So for that, we designed an application policy to sort of look at that here. You can see it has the same evaluate method, or similar evaluate method as the user policy, only with its local state and local constraints. We're going to look specifically at this hint part where, as you can see, if the playback buffer is greater than 30 seconds, the application decides that its usage is not urgent and it'll only hint that it needs a normal priority. However, if the buffer falls below 20 seconds and until it goes back above 30 seconds, it determines its usage is urgent and it needs a high network priority. So you can see we set a high and low watermark of this buffer so that it's not using too much high priority at any one time. But in order to actually incorporate this, we need a few changes to our user policy, and we've highlighted them in green here. So now, instead of just looking whether it's in the foreground, we also look at any hints that the applications have provided in previous rounds. And we see that we've added an else if here that calls out to a function that the user would write called allowed, which takes in an app as well as the hint that that application is requesting. You can imagine the user would specify under which apps can request which priority levels and under what circumstances they could do that. So if it was allowed, this application that requests for a high priority would be granted it, and then it could actually work as it had hoped. So now that we've covered the main components of Tango, we wanted to test the framework in practice. So we've built a prototype in Java that runs on Android phones. One of our interests was applying policy to new techniques like network migration. So we also used the serval network stack, which provided us with flow migration. And we explored both a single policy working with the user policy example, as well as policies that worked across applications. So looking at our first example, our use case was that we wanted to stream music while going across campus that has spotty Wi-Fi. This campus Wi-Fi serves as a good opportunity to sort of offload some data from your cell network to not go up against your data cap. Unfortunately, it can be sometimes tricky to connect to these for any one period of time. They keep breaking. Fortunately, we had network migration to allow us to seamlessly go between these networks. But even with that, we still face some problems that we need to deal with. So we had a few questions that we wanted to answer in this evaluation. The first was, how do we use policy to determine when we should switch between Wi-Fi and cellular? 2, how do we minimize cellular usage when we do use these new network switching? And 3rd, how can application policies help us in this regard? So here we have a map that I got to walk many, many times across my campus while listening to music. I started at the bottom left, going to the top right. And you can see the green is good, what we call good Wi-Fi, where I could get actually data through and my streaming could continue. The red is bad Wi-Fi, where I'm connected to the Wi-Fi, but no data is actually getting through. What ends up happening here is in a couple of these spots, my packets get dropped. I get put into a TCP timeout. And I actually miss good periods of Wi-Fi that are actually in this long period of red, because the timeouts get so long that they skip over good periods. And eventually it looks that bad. Looking at it from another perspective, here's a graph of my playback buffer in terms of seconds of music I have buffered on my phone. You can see in the light gray areas is when I'm on Wi-Fi, but I'm actually declining. My buffer is actually declining. That usually corresponds to these situations in the map where that long red tail is. You can see this doesn't actually pose us an issue in this scenario because there are no playback pauses and things seem to work all right, except that we noticed that there are areas where I had unnecessary cell usage. So here I have almost 300 seconds of music buffered, and yet I'm still using the cell network, even though I could potentially just skip it and maybe my buffer would survive. So our first plan of action was to sort of create a user policy that put a rate limit on the cell interface for this case that said, do not go any higher than about the playback rate of our music, so that it's only buffering enough to slowly build the buffer, but not enough to seriously outrun it. But this causes the first issue to actually become a problem now. So now these long declines eventually lead to pauses in playback, which is no good. And so now we needed to actually figure out how to deal with this problem in terms of Wi-Fi. So in order to do that, we decided we needed our user policy to help us improve the network switching. The main goals being we needed to be more aggressive in leaving Wi-Fi so that we don't get caught on these long periods of red zones. And we also wanted to be more conservative in joining Wi-Fi. We didn't want to join and immediately fall into a bad area and then have to jump off again. We used a couple of heuristics based on signal strength trends that we gathered through our controller's device state measurements that we couldn't normally have done. And these are based on measurements around campus. We determined good thresholds. There are more details in our paper about exactly how we chose these thresholds.
Everybody should gather in front.
If you can't see it, I can show it to you later.
I have a question for you while you're waiting, though.
What's that?
So these policies look kind of detailed and low level and everything. Is there a higher level kind of policy where you think that it will eventually go to, and this will be part of the engine of?
Yeah, I mean,
that?
I actually wrote some of these. They actually weren't as complicated as you might imagine. They're actually pretty straightforward, but we could imagine there being a
databases with the GPS to tell you about, about the terrain and all sorts of things, right?
I think that there's definitely room for things like that too.
Yeah, well, we can sort of see it.
Yeah, I
Do
mean,
your best.
where's the best place for me to stand?
That's a good place to stand.
Maybe you could ask some questions.
Yeah, well, I think we should just.
It's your session.
Yeah, okay, so we're just gonna go to Q&A, unfortunately.
Oh.
There's
There's some
if you have
really good
questions,
graphs here.
Come up to the mic and ask them. Let's thank our speaker.
For what it's worth, this has happened to everybody at some point in their career. So, it's
It's
just
good,
part of
it
life.
happened my first talk.
Okay, well, yeah.
There's no
That good.
There's no overheat as well.
Mike is dead.
Mike's dead.
Mic overheated?
No, something else happened. That's what's killing me.
It's a complete failure.
We can
So anyway, that's great work. I like it. So in another kind of domain, if you are talking about schedulers for processes, so CPU in terms of network. So when you have competing applications, then you have some kind of something like a virtual scheduler, which means you have an hierarchy of schedulers. Do you have something like this for network? Because if you want to download or customize your application with two competing policies, how does that work?
Well, we have talked about some hierarchy, like the user policy, for example, predispose settings that apply to a class of apps, like streaming apps, saying, all right, these are the constraints that would be applied to these apps. So that way you don't have to like make sure you know about every app that can be on your phone, and you can sort of group them in there. I'm not sure that it's exactly analogous to like CPU processor hierarchies, but
Well, I think one main difference here is that normally there's only a single user on a mobile,
yeah.
while on a server you could have
Sure.
competing users. Maybe the only similarity is if you download the policy together with the app. So if you download the policy with the app, maybe two competing apps may have competing policies.
Yeah, I mean, what we expect is most of the, I guess, conflicts would be between user and the app. So like if a user or an application just doesn't work with whatever the user's trying to goals are, maybe then what ends up happening is they just find an alternative app that does fit in there. So we kind of think of that as more of just like a market solution where you want to write a policy for your app that works across a broad spectrum of user policies, but if not, then it's up to the user to either think, man, my goals are too restrictive, or they might just need to find a different app that fits their needs.
Other questions?
Because you did not finish that, so some point I did not totally get it. Probably everybody get it, so let me ask this. You show the bad Wi-Fi and good Wi-Fi, but maybe the common contents you're going to telling us why the bad Wi-Fi is bad and why the good Wi-Fi is good?
Okay, so the good Wi-Fi was mostly, I guess, I mean, it's a variety of factors. I'm working outside and I'm connecting to multiple hotspots. So usually the good ones were I was close to the actual hotspot, like a building that had it. So there was low noise and things were going well. The bad Wi-Fi are probably broken down into two groups. There, when I get further away from these, like obviously the noise goes up as I get more bit errors, and so then throughput goes down. And then what ends up happening is I'll get TCP, like it'll eventually affect TCP, which will go into a timeout. And this will keep happening because maybe I'm not really close to an access point for a while. And eventually the timeout period gets to be 1 or 2 minutes long, and I actually skip over some good ones, like good to use the Wi-Fi.
Was there a policy you didn't show us that was going to say something like, don't use my cell phone, my cell connection if my buffer is a third full or more?
Yeah.
Because I felt that there was just like a skipped thing.
So that's actually where we're getting to in here. After we developed the network switching, I don't know if everybody can see this, but the first thing, we didn't do any rate limit, and obviously it works better in terms of Wi-Fi. Is the projector working? No, just. Anyway, yeah, I'll put it there. So hopefully you can kind of see this. Then what we tried with better user switching, we tried obviously rate limit on the cell interface, which works well and definitely reduces the usage. But if you want the best usage, we wrote an app policy that works sort of with the user policy. And here, the user policy gives them a constraint that says you only get this amount of data over this period of time, which doesn't mean it has to use in a rate limit fashion. It could do it burstily, like if it switches songs and wants to quickly fill the buffer. Otherwise, the application policy, once the buffer was over 30 seconds, it just didn't use the cell interface. And so then you can actually see declines on the blue part, which means it's not doing anything and the music's just playing. And then we had a graph to show the usage. And with the app policy, we're getting about 30 times less cell usage if we didn't do that. So, and even compared to the broken one of Android, we were getting less cell usage. Yeah.
Any other questions? Okay, so
Sorry, just continue my question. You give me the impression that the bad Wi-Fi is bad because the error interface, because of physical reasons. However, your solutions comes from the logic layer. You will use some policy to manage that, right?
Yeah.
Okay. So because you did not finish, so something we.
Yeah. So it's sort of like those measurements. Not necessarily that the Wi-Fi is bad there. I guess that's a bit of a mislabel, but it's that it wasn't usable for us. Like we didn't get any data through on that time. And part of that is some of them were because of bit errors, and some of them are because it was just stuck in a TCP timeout, and we didn't try on that. And so, I mean, the first problem causes the second problem. So, yeah. Once we decided to switch off more often, we're able to get only on the digital Wi-Fi.